Welcome to Spaceverse, your portal to cosmic adventures. Imagine trying to find something that makes up 85% of all the matter in the universe. More than all the stars, planets, gas clouds, black holes, and galaxies combined, and yet you can't see it, can't touch it, and it doesn't emit, absorb, or reflect light in any way. It slips through your body, your house, even entire planets and stars, without making a sound or leaving a trace. It's completely invisible, not just to the naked eye, but to even the most advanced telescopes ever built. That's the extraordinary challenge scientists are facing in the search for dark matter, a mysterious, elusive substance that doesn't interact with light or normal matter in any familiar way. And yet, its presence is undeniable. We can see its effects everywhere in the universe. It's the hidden force that sculpts galaxies, the invisible glue that keeps stars from flying apart as they spin at breakneck speeds. It's the silent architect that bends starlight like a cosmic lens, subtly warping the view of distant galaxies in ways that only gravity can explain. Without dark matter, our best models of the universe fall apart. Galaxies would unravel, clusters of galaxies wouldn't hold together, and the large-scale structure of the cosmos, the vast cosmic web connecting billions of galaxies, wouldn't look anything like what we observe. It's as if the entire visible universe is just the tip of the iceberg, floating atop an unseen, colossal foundation of mass that holds everything in place. And yet, despite its enormous influence, we've never seen a single particle of it directly. And that's why this hunt is reaching new heights, literally thanks to the James Webb Space Telescope, or JWST. In this video, we're diving into the real science and cosmic detective work happening right now as researchers use JWST to search for signs of dark matter, and more specifically, hypothetical particles known as actions. Let's get into it. Dark matter is the name we've given to something mysterious, a type of matter that doesn't interact with light. And yet, it's everywhere. Galaxies rotate the way they do, not because of what we can see, but because of the gravitational pull of something invisible. In fact, all the ordinary matter, stars, planets, gas clouds, black holes, bacteria, even us, adds up to just 15% of the total matter in the universe. The other 85% is dark matter. The frustrating part. We know it's there, we just don't know what it is. So far, scientists have only been able to infer dark matter's existence through its gravitational effects. That is, how it warps space and influences light and visible matter around it. But when it comes to detecting dark matter directly, seeing it, touching it, measuring it, we've come up empty-handed. The particles were made of electrons, protons, neutrons, all interact with light. That's why we can see things. But dark matter doesn't behave that way. It either doesn't interact with light at all or does so incredibly weakly. Because of this, scientists believe dark matter must be made of particles outside the standard model of particle physics, the framework that explains everything we currently know about particles and forces. That's where actions come in. Actions are one of the leading candidates for what dark matter might be made of. These are extremely lightweight, unstable particles which, and here's the important part, can decay into two photons, the particles that make up light. Christopher Desert, a research fellow at the Flatiron Institute, explained it this way. Actions will decay into two photons, and each of those photons has an energy equal to half the mass of the axion. Through Einstein's matter or energy relationship as E is equals to mc squared. If actions have a mass around 1 electron volt per c squared, those emitted photons would fall into the infrared part of the spectrum, which just so happens to be JWST's specialty. So, in theory, JWST could detect axion decay by spotting the resulting light. But of course, it's not quite that simple. Even though actions may decay into photons, they don't do it very often. If actions make up dark matter, they've existed since the early universe, and they still exist today. That means they must have incredibly long lifetimes, much longer than the current age of the universe. So scientists are looking for an incredibly rare process. But here's the twist. If dark matter is made of actions, then there are around 10 to the power of 77 actions in the Milky Way alone. That's a 10 followed by 76 zeros. Even if the decay is rare, when you've got that many actions hanging around, some of them should still be decaying right now and producing infrared light. And that's what JWST is looking for. Elisa Todorello, a theoretical astrophysicist at the University of Nottingham, explains why the JWST is ideal for this kind of search. It's all about sensitivity and resolution. The JWST can see extremely faint objects and can distinguish different frequencies of infrared light very accurately because it has very high spectral resolution. That's important because the photons from axion decay would appear at a very specific frequency, creating what's called a spectral line, a sharp spike in the light spectrum. This spike would stand out from most cosmic light sources, which produce smooth spectra across a wide range of frequencies. But it's not foolproof. Sometimes other cosmic phenomena, like atomic transitions, can also produce narrow spectral lines. If the frequency of axion decay happens to match one of those, distinguishing between the two could be tricky. Still, JWST's resolution gives scientists the best shot yet. That spectral line isn't just a signature, it's a map. The shape of the line could tell scientists about how dark matter is distributed across the galaxy. For example, if you look in different parts of the sky, the signal should change depending on how much dark matter is in that region. As Elena Panetti, a theoretical physicist, explains, since we have a good idea of how dark matter is spread across the Milky Way, we can predict how much should appear in different parts of the sky. By comparing results from different regions, astronomers can start to separate dark matter signals from regular cosmic noise. You might think the entire universe is fair game, but the researchers are getting strategic. Christopher Desert and his team have been comparing possible targets, including the Milky Way's dark matter halo and smaller sub-halos around dwarf galaxies. It turns out that Milky Way actions may be more promising. JWST will naturally collect more data from our own galaxy than distant dwarfs, simply because it's easier and closer. That wasn't obvious at first, but it turns out to be a key insight. Meanwhile, Elena Panetti and her team have taken a very clever route. They've been using blank sky fields, the empty regions of the sky that astronomers often ignore. For astronomers using JWST, these blank sky observations are not terribly interesting, Panetti said. But here, we found an entirely different use for these blank sky observations. The lack of bright astronomical sources in them makes them especially useful for dark matter searches. Basically, these boring sky patches are quiet enough that if an axion signal shows up, it won't be drowned out by stars or galaxies. So, what happens next? Well, this research is still unfolding. The JWST is collecting mountains of infrared data, and astrophysicists are sifting through it in search of these elusive signals. If they find even a faint spectral line with the right signature and pattern, it could be the first real evidence of actions, and maybe the first time we actually see dark matter. It's a long shot, but if it works, it would change everything. And that's it. Thanks for watching us. If you're enjoying the hunt for cosmic mysteries like this one, be sure to subscribe and stay tuned, because with every JWST image and spectrum, we're getting one step closer to understanding the invisible universe.